Thank you very much. So I promised there would be a technical talk as well, and this is it. So this is through the MIT Nuclear Science and Engineering Department, and a group that really spans across multiple departments at MIT, where our goal is really to explore the application of quantum engineering principles to nuclear energy technologies. And so specifically, we ask what tools might be available to modify nuclear reaction parameters in small-scale tabletop configurations. And this kind of challenge was laid out by Julian Schwinger where he wrote, "One must ask if any conceivable mechanism now exists or might be devised whereby nuclear energy could be extracted by manipulations at the atomic level." And so we have a large team at MIT, but collaborators at Cambridge, University of Zurich, and then various groups across the US. And there's particularly now we have an ARPA-E project at MIT on this. There's 4 of us that have devised this project. Jonah is also here today. And there's 3 senior professors involved with this effort: Peter Hagelstein, who is a theorist, Yaming Chang, who's a material scientist, and Keith Nelson, who's an expert on laser or light matter interactions. Okay, so let's think a little bit. Let's go back in history a little bit, and let's go back in time a little bit. So there was this paper in 1965 by Terhune and Baldwin that first argued that that superradiance would also apply to nuclei, and so their point was the usual assumption that each nucleus radius independently is incompatible with the coupling of the nuclei through the common electromagnetic and phonon fields in a condensed matter lattice. And in 2018, there's a very nice Nature Physics paper, Chumakov et al., where this was essentially demonstrated with a crystal involving iron-57, where a delocalized excited state was created across several iron-57 nuclei, and then the decay was a function of the decay constant was a function of the number of excited nuclei. And so this transition that you'll see quite a bit in this talk now is this 14 keV transition of the first excited state of iron-57 falling down to ground state, which has about 100 nanosecond lifetime. And so what then people do with this X-ray laser is to create this delocalized excited state that is shared across multiple nuclei. And that's from the paper now, where actual data is shown how that decay from that state accelerates as a function of the number of nuclei that participate in that delocalized state. So you see that typical pattern of superradiance, the acceleration of the decay as a function of the nuclei. And so we are interested in taking this now further and thinking about the concept of supertransfer that's already been discussed a number of times in this conference. So if we manage to transfer the excitation elsewhere before the, on average, 100 nanosecond decay, then we would be expecting to see the photon in aggregate to come out from other parts of such a sample. And so in an extension to this Chumakov experiment, you have one delocalized state, and you end up with a more spread out delocalized state. And okay, so if we want to be faster than the 100 nanosecond emission of the photon, we need to involve supertransfer. There's this kind of seminal paper by Lloyd and Mozzeni, and basically what supertransfer is if you take a Dickey model, and in this case we have excitation shared across 2 qubits and two other qubits in ground state, and then we scale this up now to 3 qubits sharing initial excitation, or 4 qubits, you see how the frequency of Rabi oscillation increases, and that's the supertransfer effect right there. And so we then have a simple analytic expression here for the sort of transfer rate that's be expected here, and you see there is the number of nuclei that participate, there is the coupling constant, and then there is the transition energy. So now this is good news, of course, because we can scale, we can increase the transfer rate as a function of the nuclei participating. But this is kind of bad news, the coupling constant and the transition energy, because when we look at nuclear systems, we're dealing with much larger transition energies. The 14 keV transition of iron-57 is one of the lowest excited states of nuclei. A lot of nuclei are in the MeV and the mega electron volt range. And then also in terms of coupling, because nuclei is so small, dipole-dipole coupling is much weaker than at the atomic level. So, so you're dealing with incredibly small coupling strength. But you can somewhat make up for, or you can alleviate that a little bit by providing an external boson field that then a nuclei couple to it at a stronger coupling strength. And so we can't work with dipole-dipole coupling, but we can work with this kind of an external, a uniform field, external oscillator that these nuclei then couple to, and then you get indirect coupling between them. And this has actually been also nicely demonstrated in this article, Bock-Lage et al., that showed 100 nano electron volts of coupling strength from an external RF field applied to nuclei. And so the logical extension or implication of this would be to place this Chumakov sample that showed superradiance inside a solenoid and apply this oscillatory magnetic field. And so that's kind of the experiment that we want to propose and work with people of the original Chumakov experiment, where basically you excite a part of the sample with the delocalized 14 keV states. You have a detector look at another part of the sample, and as you switch on the shared boson field, you would expect a super transfer and this accelerated exciton diffusion, if you like, at the nuclear level. So I'm going to show you later, we're working out the numbers. Our theorist is confident that you get millimeter level distances covered, but then super transfer alone may not be enough. But there is also, what's also already been mentioned, noise-assisted or loss-assisted enhancement of excitation transfer. So these are two kind of important papers in this regard. And so the sort of the philosophy here is that you're hindered, the transfer rate is hindered by destructive interference that occurs between the upper and the lower pathways through the virtual states that are symmetrical. But if you have selective loss that only applies to one of those pathways, then you actually get a reduction of destructive interference. And you can also model this with, if you take your Dickey model as before, and you apply a selective loss term, you can see how, in this case, the transfer rate increases. So these are the kind of tools we're working with, and we have this paper in preparation where beyond these simple toy models, there's a more realistic, a Hamiltonian with a more realistic implementation that considers the actual nuclear excited states and the various spin states of the iron-57 nuclei, and then also the more realistic nuclear magnon interaction here. So this is in preparation. Okay, so what could this kind of be useful for if we allow ourselves to dream about nuclear excitation transfer? So there's this literature on nuclear batteries, which is kind of interesting. When you mine tantalum 180, tantalum 180 has this incredibly, it has a very long-lived excited state. So essentially all tantalum 180 you find is in a metastable excited state. And you can force it to ground state, which is about 75 keV. And you can force it to ground state by pushing it up even higher into an unstable state, and then it falls down. And so people have done that with basically high energy photons. So it's not technologically meaningful because you need a lot of energy to do that, but it's kind of an interesting proof of principle. And so there's a whole community that thinks about different ways of triggering these kind of nuclear batteries. But then the question is, could a coherent process be helpful here? So the idea would be maybe to have a short-lived, low-energy isotope, and then your actual nuclear battery, and then do excitation transfer of this excitation to trigger the large energy, the high energy decay. There's also, people have looked at all kinds of isotopes. So this is molybdenum-93, which has a short, it's still metastable. I mean, it's still very long for nuclear, if you think about nuclei, but this is still not much shorter, of course, than the tantalum-180, 7-hour lifetime. So you have to, in order to work with this, you have to kind of create it on the spot through an accelerator, for instance. And then you can trigger it with actually a small transition here. But that kind of sets us up for an interesting problem. So a lot of like the nuclear excited states, especially high energy states, are very clustered. So if we now think about a helium, let's say think about a helium-4 nucleus, and we apply 24 MeV gamma, then you can think of this as a kind of a nuclear battery that's being charged. And it gets into this highly clustered excited state, which we recognize as a deuterium molecule. And that deuterium molecule will decay back into helium-4, but it's incredibly metastable at an incredibly slow rate. This has been estimated in a Nature paper in 1989. But then again, can we accelerate this kind of process? And then the good thing is also, we don't need to charge helium-4. It comes pre-charged. If in a bottle of water you have a lot of pre-charged, you have basically a lot of nuclear batteries of this metastable deuterium pairs of an excited state of helium-4. And so you want to then think about ways to accelerate that de-excitation. And so that's here also is where excitation transfer comes in. And where we want to make use of large decay enhancement factors and then also this loss assisted enhancement. And so, yeah, so in order to have any hope of seeing anything, you need a large N here. And then the idea is to flip back and forth and have super transfer. But then if you have super transfer within helium-4 and deuterium molecules, you're not getting energy out. So what you want to create some sort of incoherent decay pathway where energy comes, where the closed system turns into an open system. And so that's where heavier nuclei come into place that also have excited states around 24 MeV or 23.84 MeV. So you want to basically couple deuterium molecules then to heavy nuclei. Like we did a lot of calculations with palladium-106 as a candidate, and sort of de-excite here, excite here, and then if you give 23.84 MeV to a palladium-106 nucleus, it'll rapidly disintegrate incoherently through disintegration. So it could be, depends on the exact isotope and exact state. It can be just neutron emission or alpha emission or more symmetric fission reactions. And so we've done, in our group, we've worked with existing, based on the literature, liquid drop model codes to actually get the density of states for all various nuclei of interest. So you see the excited states of palladium-106. So what would then a system of interest look like in practice? So this is where the experimental work with the ARPA-E project comes in. So we work a lot with metal hydrogen systems like palladium with deuterium nuclei that sort of go into the interstitial sites, and they can also form in vacancies clusters. And that's where you have actually deuterium molecules that can form. And so the idea is then to provide a boson field through, for instance, laser stimulation, and then couple these deuterium molecules to resonant heavier nuclei in the environment, and then basically trigger their disintegration. And so we'd like to do these kind of experiments, but maybe in many ways they have already been done. So this is the ARPA-E program with the various performers. There are 8 teams in the US, and we are all after experiments where these kind of conditions were already met, and people observe neutrons, alpha particles, and also lighter element production. And so ARPA-E has identified this approach as potentially the ideal form of nuclear energy. The kind of control that these experiments and this theoretical approach promises is really unprecedented in terms of navigating different decay pathways. So this is a high priority project in ARPA-E. And so here we're coming back to our proposal, which we put on up as a preprint for everyone to see. So we've identified in the literature these anomaly reports where different neutron emission was reported from different metal hydrogen samples, palladium, deuterium, titanium, deuterium, and also where low Z element production was reported or claimed. So all of these papers have shortcomings. That's why there's this ARPA-E program, to have a reference experiment where this kind of work is done to the highest fidelity. But they're all incredibly simple systems conceptually. So you have your palladium or deuterium, palladium or titanium sample. You introduce about 2 bar of deuterium gas, and then you irradiate it with a laser. You see a very simple setup here. And so here's some data from the literature that's been reported, where you see a neutron. These are neutron counts per minute over a longer period of time. You see before the experiment, you get the typical neutron background. And then during the experiment, you get 2 very significant bursts of neutrons coming out of this kind of system. And the other type of observations that have been reported from these systems is, this is actually from a sample that you just saw in that photograph, a palladium thin film on a silicon substrate, where when you do the EDS analysis, you see the palladium peak, a little bit of silicon as is expected from this kind of sample, but this was irradiated just with a 5 milliwatt laser. You see a morphological change, which is already puzzling, but then not only that, in the morphological change, the palladium peak has gone down, and you have these lighter elements, and they actually happen to be there. They happen to be all the expected daughter products from the different stable palladium isotopes and the other respective daughter products to form the pairs. So we think these are very interesting indications that there is indeed an induced fission process of disintegration of palladium. And what determines whether you get more like symmetric fission or just neutron or alpha emission, it depends on how much energy you transfer to these heavy nuclei. This is known nuclear physics, nuclear molecule, nuclear cluster literature, depending on how much energy you pass to a nucleus. And basically, generally, the more energy you pass, the more symmetric your disintegration is. So we think what might be happening in these experiments is that where you have neutron emission, you get just the excitation of palladium, and that disintegrates then to another palladium isotope through neutron emission, and where you have these low Z elements, you actually end up going to higher excitation. You need to go to higher excitation to get some more symmetric fission, and so you have somehow stronger acceleration of the process, and so you get to step up and then disintegrate more symmetrically. So we view this as a kind of like boring a tunnel from 2 sides. There's this modeling and simulation effort, and then there's the increasing the quality of these experiments. And so eventually we want to move towards a quantitative picture. This is kind of the outline of where we can relate experimental parameters to actually expected reaction rates here. And then really the table of nuclides is the playground then, because you can look at all these different isotopes and their excited states and how they respond to these kind of processes and how they disintegrate. And so here we've done a little bit of that just by looking at the different excited states across different these are all stable palladium isotopes in their lifetime. So of course you want long lifetime excited states such that they can participate in the coherent dynamics. Okay, so that's the summary then. So we start with existing work, superradiance demonstrated at the nuclear scale. We want to extend that to supertransfer with a simple modified Chumakov experiment where one uses the same kind of iron-57 crystals, but then there's potential for this to be an explanation for these anomaly reports. And ideally, we would like to see a new form of nuclear engineering, which would be quantum augmented or coherent nuclear engineering.